Subnetting, the fun one. In this session, we're going to be looking at subnetting. We're going to be looking at networks, we're going to be looking at hosts, we're going to be looking at the binary. So we've got a bunch of bits that make up the network portion. We've got a bunch of bits that make up the host portion. And we're going to use those bits to calculate how many networks we've got, how many hosts per network we've got. And then we're going to look at variable length subnet masking, which is actually subnetting an existing subnet even smaller than it is. And then we're going to have a look at the way we do it in IP version 6 as well. So, why do we need to subnet? Broadcasts in your network are bad. We've got to get rid of those broadcasts. If we've got a large network with lots and lots of broadcasts mucking around, then that's going to cause us a problem. But we could also have security reasons. We might have a bunch of IP cameras or telephones or servers or systems we want to keep separate from each other. So we use the subnetting to separate large blocks of users into smaller blocks for the broadcasts, and we also use it to separate by different types of roles or privileges or device types or what they're trying to achieve. When you're looking at planning for your network, think about how many hosts you're going to need to have in each network. Think about how many networks you are planning on creating. How much actual address space do you have to play with? So let's look at some of the basic rules that we need to think about when we're planning for getting a big network and chopping it up into smaller pieces. All IP addresses are 32 bits long. IPv4, 32 bits long all day. The IP address is made up of two halves, the network portion and the host portion. The subnet mask tells us which half is which. So we've got a bunch of network bits and we've got a bunch of host bits. You are allowed to borrow from the host bits, but no matter how many host bits you borrow, you must always leave 2 bits behind. 2 host bits must remain. Once you've borrowed some bits, those new bits are subnet bits. So 2 to the power of however many bits you borrowed is the number of subnets you've created. How many host bits are left behind? 2 to the power of h minus 2 is how many hosts per subnet are left behind. It's minus 2 because you can't use the first, you can't use the last, because the first is the network ID and the last is the broadcast address. So we started with 24 network bits and 8 host bits. We borrowed 3 of those host bits and made them now subnet bits. So 2 to the power of 3 equals 8. So we have created 8 new subnets. And there are 5 bits left over. So 2 to the power of 5 minus 2 equals 30. So we started with nothing and we had one network with 254 hosts. We borrowed 3 bits. We now have 8 new networks, new subnetworks. And each of those has a maximum capacity of 30 hosts per subnet. So let's have a look at this example now. We start off a 192.168.1.0 normal standard network. We've chosen to borrow 1 bit. And that 1 bit has now provided us with 2 subnets. The first subnet, subnet 0, gives us a range from 0 to 127, where 0 is the network ID and 127 is the broadcast address. And the second subnet is subnet 1, which starts at 128 and goes all the way up to 255. So 128 is the network ID and 255 is the broadcast address. Notice the mask. Before we started, the mask was /24. But now our mask is /25. So 255, 255, 255, 128 is actually 25 bits in the mask representing the network portion. We've borrowed 1 bit. So let's allocate these to devices. So we've got subnet 0 is on the top and subnet 1 is on the bottom. So whenever you're doing subnetting, you always do 4 things. You need the network ID, the first usable host, the last usable host, and the broadcast address. So look at these 2 sections. We've got 192.168.1.0 for the network. 192.168.1.1, first usable. 192.168.1.126, last usable. 192.168.1.127, broadcast address. Now for the next subnet, 192.168.1.128. That's the network ID for the second subnet, or subnet 1. Then the first usable is 129. The last usable is 254, and the broadcast address is 255. The purple number in the middle, that is a representation of the network ID. The top one, it's 0, and the second one, it's 1. What would happen if we borrowed 2 bits? 2 to the power of 2 equals 4. So we created 4 subnets. But there are only 6 bits left over. So therefore, we only have 62 possible hosts in each of those subnets. So let's look at the way it's broken down. Now we just look at the network IDs. This is the way we summarize and make sure everything's fine. So subnet 0 is 0. Subnet 1 is .64. Subnet 2 is .128. Subnet 3 is 192. So if we were to look at the host ranges, we would have subnet 0 would be 1 to 62. Subnet 1 would be 65 to 126. Subnet 2 would be 129 to 190, and subnet 3 will be 193 up to 254. Because remember, the network ID is shown there in green, and the broadcast address is the highest possible number. So net 0 broadcast is 63, net 1 broadcast is 127, net 2 broadcast is 191, and net 3 broadcast is 255. And notice the mask. We have a new subnet mask, /26, which is 255.255.255.192. What would happen if we borrowed 3 bits? 2 to the power of 3 equals 8. So now I've created 8 subnets. So let's break it down. So subnet 0, we got from 0 is the network ID, 1 is the first, 30 is the last, 31 is the broadcast. 32 is the network ID for subnet 1. Then 33 is the first, 62 is the last, and 63 is the broadcast. The one after that, 64, network ID, 65 is the first, 94, and so on and so on. Notice the purple. The purple is counting up the network IDs. So for net 0, they're all zeros. For net 1, it's 1. For net 2, it's 2. For net 3, it's 3. That's the binary equivalent. It's only after we need to convert that binary back to decimal. Remember, the decimal is just for us humans. The router reads everything in binary, so it doesn't care. The decimal is just for us humans. So let's look at the first usable for subnet 3. 192.168.1.011.00001. And if you add those characters up together, they equal 97. So we're taking the binary, the subnet ID, plus the host, converting that back to decimal to get us to that 97. Going on, because we created 8 networks, so that previous slide was the first 4, and this is the second 4. All the way up to the very tippity top, where the network ID is 111, and the host portion is all ones, and that's 255. So this is why we spend a lot of time converting from decimal to binary, binary to decimal. It's for this, it's for subnetting. So how do we actually allocate these addresses to our networks? Well, here we go. So subnet 0 is at the very top, PC1, it's the host on subnet 0 and the gateway of .1 on gigabit 0 on router 1. Then subnet 1 is the second one for PC2, .34 with .33 as the gateway. And then subnet 3 and 4 and so on and so on. Now, when you're doing subnets, just a bit of a tip and a trick to make sure your math is correct. Subnet 0 always ends with always is 0. That's normal. All network IDs, the names of the networks, are always even numbers. Always. Because look at the network IDs. 192.168.1.0, 192.168.1.32, 192.1.96, 192.168.128, 192.168.1.64. They're all even numbers. Each subnet is a multiple of subnet 1. So for example, subnet 1 is 32. That's the size of it. So from 0 to 31 is the first subnet, and 32 is the number of the subnet 1. So each subnet that we've created has those, that's the size of it. So subnet 5 is 160. Just something to think about. Now, when you're planning for your network, there are two big considerations. I already mentioned it in the opening summary. You are either subnetting because you need to have a certain number of networks, or you are subnetting to cater for a number of devices or hosts or usable devices in each subnet. So you might look at a network and say, I need 7 networks. Or you might look at a network and say, oh, I got 50, 50, 50, 50. I need 50. I need networks that'll fit up to 50 devices in them. So you plan for the number of subnets to make, or you plan for how many hosts are going to fit inside that subnet. And as we looked at before, the formula for the usable host is 2 to the power of h minus 2. So if you've got 5 h's, then you can only have 30 hosts, because 2 to the power of 5 minus 2 is 30. It's minus 2 because you can't use the first and you can't use the last. The first is the subnet or the network ID, and the last is the broadcast address. This is where we're looking at the second example of thinking about the number of networks. So what do we got? 1, 2, 3, 4, 5, 6, 6. So we need to think about how many bits do we need to make 6 subnets. We don't know how big they are, but that's not the factor. The factor is number of networks. So in this example, now it's number of hosts. So we've got 40, 20, 20, 20, and 15. So this is the math we need to think about. How big do we need to make our subnets so they're going to fit in this number of hosts? And it's always a good idea to plan for a little bit of growth. In this example, this is where the binary and the decimal and the math really starts to kick in. And this is why we spent so much time doing the binary. And if you haven't, you need to practice your binary, and that's what we'll be doing today as well. We started with a /22. Now the /22 doesn't line up with the dots because the dots are 8, 16, and 24. So now we've got to do everything in binary and then convert it to decimal after we've done it. So we're going to borrow 4 bits. And notice those 4 bits span over the dot. So the first 4 subnets are 172.16.0. But then subnet 4, 5, and 6 and beyond, they cross over to the other side of the dot. So now it's 172.16.1 and 172.16 all the way up to 172.16.3 dot something. So this is why you always do subnetting in binary first. You do it in binary first, and then you put the dots back in and convert it to decimal after the fact. So notice here we've got borrowed 4 bits, so 2 to the power of 4 is 16. We've got 16 possible subnets, and we've got 6 bits left over. So 2 to the power of 6 minus 2 is 62. So that gives us 62 hosts per subnet. Now traditional subnetting is pretty straightforward. You just keep chopping your networks in half until they fit the right size. So here we've got 1, 2, 3 bits borrowed. which means we've got 30 hosts. We've chopped our network up into 1, 2, 3, 4, 5, 6, 7, 8, 8 little perfect wedges. But not all the networks are going to be 30. Some of them might be 5, some of them might be 15, some of them might be 20. So we've got wastage. We've got IP addresses that are wasted. And more particularly, our WAN links. Whenever you have links just between two routers, typically you only have 2 IP addresses, you know. So if you've got 2 IP addresses, you've actually got 28 wasted if you've got a perfect subnetting scheme like this. So what we're going to look at later on today during the labs is subnetting the subnet. So that's what VLSM is. You take a subnet and you chop it up even further. So you might start off with a subnet that's got 30 hosts. You might say, actually, let's just grab that subnet and cut that one subnet in half. Okay, sure, we'll chop that in half. Or now one of those halves, we're going to chop that up again. In this example, we've got our 30 subnets, our subnets with 30 hosts, and we've picked one of them and we've chopped it up into 8 individual chunks. And each one of those 8 chunks only has the capacity for 2 hosts per network. And these are perfect for our WAN links. So VLSM, or variable length subnet masking, is just subnetting a subnet. So I give you a pizza, I come into the room and there are 50 of you, and I bring in a pizza and I cut it in half. And I say, half this pizza for me, the 50 of you, that half's for you. So then the biggest and the strongest cuts that in half and says, well, this is for me. So you guys can have a quarter, and you have to chop it up in yourself. This is what all VLSM is. You start with the whole, and you chop it up, and then you take the pieces you've already cut out, and then you cut them in half again. So here's a good example. We started with a /24. So we borrowed 3 bits, and that was going great. And then we realized, actually, you know what? We need some more pieces. So we took the very last piece of pizza that we chopped up, and we chopped that up even further. And that's pretty much the same example based on the image from the previous slide. VLSM is just subnetting a subnet. And we're going to do lab exercises on this in class. And I'm also going to make another video just on VLSM, which will be similar to the examples that you'll be doing in your lab books. And here's how we put it all together. We have 4 buildings or subnets, and between those buildings we have WAN links. Now, as I pointed out before, a link just between 2 routers only needs 2 IP addresses. So that's why a /30 is perfect, because it only allows for 2 IP addresses. So in building A, we got a /27, in building B, we got a 27, C, we got a 27, and D, we got a 27. Nice big networks. And the stuff we left at the end that we chopped up, they're our little tiny little WAN links, /30, /30, /30. This is also where our decimal to binary comes into play, because you're going to see networks that say /27, and you have to think to yourself, oh, what's that? 27, so that's 24 plus 3, so therefore that's 3 ones. So what is 1 1 1 0 0 0 0 0 0, and convert that to binary to decimal. So there's a little trick you might want to try and memorize that we'll go through during class time, but I'll just go through it briefly now. Just hold up your hand, your left hand, or if you're right-handed, hold up your right hand. Sorry, hold up a hand. So your thumb is 1, then your index finger is 2, 3, 4, 5, and then the thumb on your opposite hand is 6. So just look at those fingers. Look at them now. Thumb, index, middle, ring, pinky, thumb. Now look at them again, and in order, from thumb through to your other thumb, say 128, 192, 224, 240, 248, 252. I'll say it again. Your thumb is 128. Your pointer is 192. Your middle finger is 224. Your ring finger is 240. your pinky is 248, and the other thumb is 252. That sequence is how you can quickly convert to the subnet mask. So when you say /27, you hold up your hand and you go 1, 2, 3. Okay, thumb, pointer, middle. That's 3 bits I need. So therefore, 128, 192, 224. Okay, the mask is 224. And now we got a /30. /30 is all 6 fingers. So that's 128, 192, 224, 240, 248, okay, 252. The mask is 252. This is a little shortcut you can do. Obviously, if you've got a pen and paper, then just write them out, convert it from binary. Just write 1, 1, 1, 0, 0, 0, 0, 0, and convert that from binary to decimal. Pretty sure you'll get 224. So if you memorize it, that might speed up your calculations. Now, IPv6 is nothing to be scared about, because 99% of the time, you are only ever going to be given 2 or 3 blocks. IPv6 has 4 blocks in the network portion by default. No one in their right mind is going to, in this level, in this stage of your subnetting and IPv6 career, is going to make you do anything more challenging than that. So, you might be given 2001 ODB8 ACAD. Now you know there's a 4th block there. So that 4th block that's it. That's wide open to do whatever you want. So you could literally create 65,536 subnets if you want. And that's quite fine. So if you get a /48, that tells you that you've got 16 bits to play with. So whenever you try and subnet with an IPv6 address, you just say to yourself, oh, well, they've given me the first 3, so therefore that 4th block, that orange block is wide open. I'll just make, 1, 2, and 3, or 111 and 222 and 333, just whatever you want. So when you're subnetting IPv6, that's all you got to do. You've given 3 blocks at a /48, you just make up the 4th block, and then that's completely legal, normal way of subnetting IPv6. IP address, 32 bits long. When you borrow, you must leave at least 2 bits behind. The bits you've borrowed create your subnets. The bits left over in the host portion is your hosts per network. So, same example as before. We've got, well, we haven't borrowed anything. So we've got just the network with 254 available hosts. That's a classic Class C address. So if we borrow 1 bit, then we've made 2 subnets, and we've got 2 to the 7 bits left over, so that's 126 hosts per network. If we borrow 2 bits, we create 4 subnets. We've got 6 bits left over, so that's 62 hosts available per subnet. We borrow 3 bits. We create 8 subnets. We have 5 bits left over, so we have 30 hosts per subnet. We borrow 4 bits. We have 16 new subnets and 14 hosts for each one of those subnets. We borrow 5 bits. We've got 32 new subnets, and each subnet has 6 available hosts per subnet. And if we borrow 6 bits, we've got 64 subnets, but each of those subnets only has 2 available hosts per subnet. What about if we have a different class, like a Class B network, where we've got one big network with 65,534 hosts per network? Well, that's ridiculous. The broadcast will just cripple that network. It'll be unusable. So let's do some basic subnets. Let's borrow 4 bits. So we borrow 4 bits and we get 16 new subnets, and each one of those 16 new subnets, we have 4,094 available hosts per subnet with a /20. That's the mask, because there are 20 bits, because we've got 8, 16, 17, 18, 19, 20 network bits. But 4,094, that's still a pretty big network, and that's a bit crazy. So what most people do is just get your class B network and chop it up at the dots. So for us humans, we can figure it out. So we borrow 8 bits and we've got 256 subnets, and each subnet has got 254 hosts, and we don't have to bother about which side of the dots we're on. So this is what you do if you're planning from scratch and you're lucky. But in the industry, you might come across a network that's already been chopped up before you get there. So you might have to be a little bit more creative, and you may have to blur the lines from where the dots are, and then you have to do it all in binary, and that's fine. So, subnetting, we need it. Networks are too big, or we need to separate by design or region or equipment or role or device type. We need to chop our networks up. We can do straight normal subnetting, just chop, chop, chop in equal pieces, or we can do variable length subnet masking where the pieces are not the same size. IPv6 is very straightforward because you're always going to get those first 2 or 3 blocks, and you've got a whole block to play around with at the end. When you're thinking about subnetting, size, location, we've already talked about that, and always got to test stuff out. So, thanks for watching. Please remember to subscribe, click the notification bell. If you enjoyed this video, give me a thumbs up, and leave me a comment with what you'd like me to make for my next video. I'll see you in the next one.